Welcome in the world of artificial intelligence under artificial intelligence using Python series of lectures. This is lecture on search methods part 1A. Hi, I am Dr. Sunil from GCS Solutions. In this lecture we are going to see the state space search, that is the concept of state space search. Then we'll see what is single agent search or a goal directed agent, and we will also see the state space search examples. So before we get into the state space search algorithms and try to elaborate what state space search is, we will first try to understand or clear something about the state space search. That is the terminologies involved in state space search. Now, what is state? State is description of the world in which the problem solver operates. Now here we need to understand what world is. World is the problem which is to be solved in the context of AI. For example, if I am trying to solve 8 puzzle problem, or if I am trying to write some intelligent program for 8 puzzle problem, then that problem for which we make a description, that is the world. So I call this problem as a 8 puzzle world. Suppose you have 8 queen problem to be solved, then that particular problem is called 8 queen world. Now world is nothing but the problem to be solved, and problem solver is the actual program which basically solves the problem. This problem solver is an intelligent program. Now here state space, it is a space in which each element is a state. Now if you see here where I'm pointing or focusing with this highlighter, so here you will find the larger circle. In that larger circle is the state space boundary. Now in this state space boundary there are various states. So each of these circles, various circles around, there are some order 25 to 27 circles. So all I call these all each of these circles as a state. Fine. Next is start state. Now in these various circles you'll find typically different marked circles. Like there is a green circle which is called a start state or initial state. This is the state with which the actual searching starts. That is the starting point. Uh, we may call it as a starting configuration also. Goal state is the state which is a desired state, which the problem solver wants to achieve. Now this goal state can be one or more than one. Now we'll make this thing more clear while we'll be dealing with the examples under this state space search. For now we have to just remember that a goal state can be one or more than one state. What is an agent? An agent is a program which is nothing but the problem solver. We call that program as an agent that makes decision and takes action to change this state so that agent can move to the new state. If you see this figure here, agent is a program which will start with the initial state. Now with the rules which are basically written in terms of the programming steps, with those rules this agent takes the decision. It decides uh, what should be the next new state if the current state is not the goal state. The ultimate goal of this agent is to reach to the goal state. Now here if you see this green color, sorry, this blue color arrows, these are the transitions from one state to another state, and these transitions are made by the agent program depending on the rules which are described in the program itself. Now what is the task and task or plan? These are the sequence of actions or moves to be taken by the agent program to get the desired goal state, because once the program a problem solver starts with the initial state, and if it tries to lead to the goal state, there might be so many intermediate states, and there might be certain prescribed steps to be followed to reach from the start state to goal state, and this task or plan is also called as a solution plan. Now here we'll try to understand the state space search. We have already seen some of the terminologies. Now what is state space? State space is essentially consists of set of nodes representing each state of the problem. Here if you see the same diagram which we have already seen in the earlier slide, so here this larger circle represents the state space, and in this larger circle there are 23 small circles which are called states, and each state is called a node. Now here if you see this blue color arrows, that is the arcs, these are the legal moves or actions to be taken. Now these moves or actions to be taken are decided by the rules which are described as a part of the agent program. Now here there are various circles. You'll find green circle as the initial state, then this blue arc as the transition from some state to another state, and to make transition from say initial state to the goal state, there might be so many intermediate states which basically the problem solver will consider as a part of the legal moves and will lead to the goal. Now to do this, that is searching of the goal state, search is the process of considering various possible sequence of operations applied to the initial state and finding out the sequence which ends in the goal state. Now here whatever steps I was talking of, the steps which are taken by the problem solver to find out the goal state, this entire journey is called a search. Now here whatever intelligent steps are taken by the problem solver, that those steps or that particular program is called a search. Now here we will be dealing with these search problems wherein an intelligent agent will always try to find out the given goal, and this finding of the goal depends on the given problem that we'll see as the part of examples under state space search. So we'll see it very soon. First of all, we'll finish up with the other terminologies in the context of the state space search. Now this search problem is to find sequence of actions which transforms the agent from initial state to the goal state. Now here search problem is basically represented by four tuples, that is S, S naught, A and G. Now we'll try to understand this set of four tuples, because to solve the actual given problem, and this actual given problem which is the intelligent program can be for any scenario in the real world. For example, you may solve 8 puzzle problem, you may solve I mean to uh, say 8 queen problems, or you may solve even the Tower of Hanoi problem, or you may solve even some game problem like tic-tac-toe. So if we see these different problems, we'll find that we need to have a proper formulation of all these different problems in a common way of representation. Now that common way of representation is basically done using these four tuples, that is S, S naught, A and G. Now if you see here what this S is a full set of state space. Now whatever diagram I have shown here, this is a state space diagram which comprises of 23 states. So this S is nothing but the set of states. So here all these different circles, including this green circle as initial state and this red circles at the goal states, these are the different states which can be considered as a set S. That is the state space. What is S naught is the initial state. So in this state space diagram, this green circle is the initial or the start state. Next is what? A. A is called as an action. Action is nothing but transition from one state to another state. If you see here where I'm pointing now, here you'll see the three different arcs going from some circle to three different circles. So these actions These actions are defined in such a way that, like, if you want to go from state I to state J, you need to perform certain operations, and those operations are basically performed based on certain rules. And if you make transition from one state to another state using uh, certain rules, that is called as the action, and that action can also be represented as a plan P. Now what this plan P is? P is nothing but the set of different actions, like A naught is the first action, A1 is the second action. Likewise, you can have n number of actions to be performed, and these n number of actions are defined based on the rules, which we'll see in the examples. You need not worry now. Now what is G? G is a set of final state or goal state or states, and if you see carefully, this G, which is the set of goal state, is always a subset of the original state space search S. Now even if you see here, there are 23 states. Of this, only 3 red circles are the goal states, and if you see this, these 3 different circles are the subset of the entire state space, which comprises of 23 states. Hope you understood, and I will make this thing clear in the subsequent discussion. Now we'll see the solution plan in details. Solution plan is represented using set of tuple, that is S, capital S, S naught, A and G, which we have already seen. Now the solution plan is a path from initial state to the goal state. A plan P is a sequence of actions. So this plan P can also be represented as a set of actions A0, A1, A2 up to AN, which leads to traversing a number of states S0, S1 up to Sn plus 1. Now these states basically belong to the goal state, because whenever the solution plan is used by the agent program, so it will perform any of the legal actions from A0 to A1, and it will traverse through different states like S0 to Sn plus 1, but some of the states will be always the goal state. That's what is the aim of the agent, to find the goal. Sequence of states is called a path. Now whatever sequence of states uh, are followed by the agent program, that is called path. For example, in this given graph, focus here where I'm pointing now. This is a graph represented as a tree. Now node A is connected to B and C, B is connected to node D, E and F. This way the connections between different nodes is a relation between different nodes is represented. Suppose that the agent starts with the start node, which is represented as A, which is yellow node. Then as A is not the goal, so it will follow some path. Suppose it happens to visit node B. B is also not goal node. Now from B, the valid moves or actions are transition from B to D, transition from B to E, and transition from B to F. Now if it happens with this agent program to select E as the next node, now E is the goal node. Now in this entire transition from start to goal node, the nodes visited are A, B and E, and this is called a path. Now path may also have a cost. Now the overall path cost is nothing but the sum of the cost of each action. For example, action from A to B costs 5 unit, action from B to E costs 3 unit. So the overall cost from A to E will be 5 plus 3, that is 8 units. So we have already seen what state space search is and how it is represented, and some other relevant terminologies. Let us now try to understand the goal directed agent. It is also called as a single agent search. Now what agent is? Agent is a software program which does some specific actions to achieve goal. Now here, the overall intention of writing an intelligent software program is to do some intelligent task, and that program is agent. We have already seen this thing. The goal directed agent aims to achieve certain goals. The overall intention of writing goal directed agent is to achieve certain goals like solving the 8 puzzle, then solving n queen problems, or say 8 queen problems, or solving even tic-tac-toe problem, or there are so many other problems which require some intelligence. Now here an agent tries to reach to the goal using some actions, which we already seen. So each state is an abstract representation of the agent's environment, and that abstraction denotes a configuration of the agent. So to understand this, let us now see this diagram where I'm pointing here, that here is the agent program which works in certain environment. Now what this environment is? Environment is a particular problem scenario wherein this agent works, and in that scenario what this agent tries to do is it starts with certain start state, and the intention of agent is to reach to the goal state, the specific goal which is basically defined by the problem designer. Now here the agent takes some input from the environment which is called as a percept. Now agent program has certain rules defined inside the program itself, and considering those rules with which it takes the set of actions and it makes the changes in the environment. That means if it is at the initial state, using certain action it will reach to the intermediate state, and eventually it may lead to the goal state. If we see this scenario carefully, the goal directed agent is also represented as a state space search scenario. So whatever we have seen as a part of the solution plan in the earlier slide, the same solution plan can be applicable or mapped with the given goal directed agent. Now this goal directed agent is responsible for solving so many various problems and so many specific goals. So here this goal directed agent will be having initial state, as we have already seen. It will be having actions and operators with which it can change its state from initial to the goal using intermediate states. So that means it can be at the current state and it can reach to the successor states, which leads ultimately to the goal state. It may have a plan, or it has basically a plan which is a sequence of actions, and this action or operator is also called as a successor function. So whatever action and operator rules are used, those rules are called as the successor function. Let us now try to understand this single search agent concept using some examples. The first example is 8 queens problem. More general, this 8 queens problem is a n queens problem, and we have to formulate this problem. And what is the way to formulate this problem? It is the standard way which we already seen in the earlier discussion. That is to formulate this as a 4 tuples. That means it should have a set of states, it should have an initial state S0, it should have some action plan A, and it should have a goal set of goal state G. So here what are these states? States, that is arrangement of this board wherein you can have no queen on the board, you can have only one queen on the board, or 2 queens, 3 queens, or at most you can have 8 queens on this 8 by 8, that is 64 cell size board. Now initial state, initially this 8 by 8 board will be a blank, that means there will be no queen placed on the board. And what is the successor function? Successor function is that you can add a queen in any square of this 8 cross 8 64 squares. Now what is the goal? Goal is to place all the queens on the board, but none of them attack either vertically, horizontally, or diagonally. So this is the goal. Now here, if we observe this carefully, this game carefully, initially there will be a blank board with no queen placed. Now that initial configuration can lead to 64 successors. That means first queen you can put on the any square. You can put, for example, if you see this diagram, so you can put first queen, for example, in the first column, third row position. Then you can put this queen at first row, first column position. You can put this queen at first row, say fifth column position. Anywhere you can put first queen. Once that first queen is placed properly, what next is that second queen is to be placed. Now we have only 63 squares left. So in that particular 63 square, we can put our second queen at any place. And this way you can get a different states at each level. Initially, there is no queen placed in any of the 64 squares. Then you place first queen at any of the 64 locations. Once that particular location is chosen, that location will again generate 63 new successors wherein the second queen can be placed. So this way this entire formulation is done, and for this you can write an intelligent program. The next problem we see under this single search agent is the Tower of Hanoi. Now we will try to formulate this Tower of Hanoi problem using our same standard representation. What is the state space? So state space will be the representation using three pegs ABC and three disks of three different colors, green, blue, red. And what is the initial state? Initial state is like a smaller disk is lying on the larger disk. So rule is that no larger disk should lie on the smaller one. Only smaller disk can lie on the larger one. Now if you see this diagram, so there is initial state. So here in my case I have shown here all the three disks of the same size, but in practical case you'll find that red color disk which is lying at the bottom is a larger one, then blue will be the smaller than the red one, and green will be again smaller than the blue one. So this way you can have three different disks. What is the successor function? Successor function is the function which helps us to move any topmost disk on any needle to topmost position to any other needle. That means we are moving from this from one peg to another peg. So here peg is A, B and C. So you can move this green color disk to either peg B or peg C. So this way. But ultimate goal is that we want that all these disks which are here at peg A should be placed in the same sequence in peg B. So it is represented here. If you see the diagram where I am right now focusing, the goal state is same as the initial state, except the three disks are lying at peg B. All the three disks are in peg B. And to do this, we can have various different states. For example, if you see this right side diagram, which is quite faint, but I hope that it is visible to you. So our aim is to transfer the uppermost topmost disk to any other peg. So if you see this diagram, here you'll find that the smaller disk can be either moved to peg B or it can be moved to peg C, once you have chosen this particular state, that is the larger disk is on peg A and smaller disk is on peg C, then you can have probable movement of moving the smaller larger disk to the peg B and then moving this smaller disk which is at peg C on peg B, and this way you get the goal configuration. So this way you can have a different states. Next is Edpuzzle. So here you will be given the board configuration with 8 tiles. So if you see this particular diagram, so this table, rather I'll say table sort of thing, this is not exactly the table, this is the board with 8 different tiles. Now in this board you'll find that there are certain numbers, so these are 8 numbers. The board is of what size? It is 3 cross 3 board, wherein we have 9 tiles and 8 tiles are numbered. We have to move or shuffle these tiles in such a way that we should get a goal configuration. A goal configuration is your number should be arranged in this sequence: 1 2 3 4 5 6 7 8. Now here, what is the initial state? That is the randomly shuffled tiles. So here, in initial state you will find the numbers in sequence 1 4 3 6 2 8 5 7. But what is the goal? Goal is to make shuffling in the initial configuration in such a way that it will match the goal configuration. So every time we'll be moving one tile either left or right or up or down. That is the successor function, wherein you can move the blank space. For example, if you see this state space representation, see the diagram where I'm pointing, it is a tree representation of the state space. So assume that initially you have 1 4 3 6 2 8 5 7, this as the initial configuration, and your goal is to arrange this. So what you try to do is you try to move this space which is represented as a black tile. So you move this space either to the up moving 4 down, or to the left moving 7 right, or the space down moving 8 up, or space right moving 6 left. That is, this way you can have any of this configuration. Once you have chosen, for example, this leftmost node of the second level of this tree, you can have again some movements, and each time you'll be getting a new configuration, and each of the uh, I mean to say the configuration can be tested for the goal state. Now here there involves a path cost. Why? Because the game is to be solved with minimum number of shuffling of the tiles. That's why if you make a move, it will cost 1 unit. The more number of moves you make, more, I mean to say, penalties you will be getting. Next example is theorem proving example. Suppose I want to prove that x plus y plus z in bracket equal to y plus z plus x in bracket. So what we are trying to prove here is mathematically x plus y plus z, that is the composite addition, is equivalent to y plus z plus x. Again, z plus is this composite addition. That's why we have put here the bracket. That means you are getting the same result. Now, to prove this, you are given certain rules. First one is the associative. That is, if I say L plus M plus N in bracket, that is same as L plus M in brackets plus N. Okay, so here we are using some associative rule. Okay, so we are trying to associate different terms, that too in proper sequence. So this is rule A. Now what is rule B? M plus N is a same as n plus m. That means 3 plus 4 is same as 4 plus 3, because addition of these two numbers in any sequence will give you same result. Now here you can have the start left hand side expression x plus y plus z in bracket. If you apply rule C, so you can interchange y plus z and x. So you can write something like y plus z in bracket plus x. It is same as this thing. If you apply rule A to this x plus y plus z, that is y plus z in bracket, if you apply rule A, it will be x plus y plus z. So this way you can have this transition diagram. So here is the transition. These are different state space elements or nodes, and using these rules like rule A and rule C, if you try to make a transition using successor function, which is defined using rule A and rule C, you can easily prove this statement, that is x plus y plus z in bracket equal to y plus z plus x in bracket. So we will be dealing with these examples while solving some problems using specific algorithms of AI under single search agent topic. So that we'll see later, but here our overall intention to understand how the problem formulation is done for any given problem so that we can write a single search agent program. Next one is tic-tac-toe. So here tic-tac-toe problem is also called as cross and not problem. So here there is n cross n board, which is the initial state, which is empty, and successor function is that any player can put cross if he is a cross player at any empty position of the board, or a player can put not in unoccupied position if sorry, it is a not player. Now here this is two player game. The goal is that player who can first get 3 of his symbols in the same row or same column or diagonal, he wins. Now this same thing can be represented as a state space, which is represented here in diagrammatically. For example, the current scenario of the game is like the cross player has made 3 crosses and the knot player has made 3 knots in 3 different unoccupied cell positions. Here, if it is a turn of the cross player, so cross player may put cross here at the third row and third column position, or he may put cross here at the second column third row position, or he may put this cross at third row third column position. Now the last example we see under this single search agent is the water jug problem. What this water jug problem is? This water jug problem is that we are given 3 jugs measuring 12 gallons, 8 gallons, 3 gallons and a water faucet. What you need to do is to measure exactly 1 gallon of water. We don't have any 1 gallon capacity jug. Here the states are like jugs filled with water with different measures. You can either fill 8 gallons water jug or 12 gallons water jug or 3 gallons water jug. Now using any of this, you have to measure exact 1 gallons of water. Now initial state, all 3 jugs are empty. Successor functions that you can transfer water from jug I to jug J with capacity CICJ and the containing GI and GJ gallons. Here for our example, assume that this jug I is 12 gallons and jug J is 8 gallons. So here The capacity of this I jug is represented as Ci, which is 12, and the jug J, which is 8 gallons, is represented as Cj. These are the capacities, and these jugs are G12 and G8. Now here, suppose I want to transfer water from jug I to jug J. So jug I will be having max of 0 or 0 comma Gi minus Ci minus Gj gallons of water, and jug J will be minimum of Cj comma Gi plus Gj gallons of water. That means suppose I have filled a 12 gallons jug, so I can transfer water of this 12 gallon jugs to 8 gallons. So if I do this, what will happen is like a 12 gallons jug will be having 4 gallons remaining, and your 8 gallons jug will be filled completely up to its capacity. Fine. So applying this, we can fill jug I, leaving it with the Ci gallons of the water. Now goal test is some jug contains exactly 1 gallon of water. And what is the cost function? Charge 1 point for each gallon of water transport and each gallon of water filled. Why? Because you need to perform this task within very specific time, and that too minimum number of transfers. So this way any given problem can be formulated using the standard formulation process like states, initial states, successor function, goal test function, and cost function. Now these are not actually the algorithms. This is just the problem formulation. We need to learn so many sophisticated algorithms under this single search agent, and these examples we will study with the algorithms in the subsequent lectures. So dear learners, how was the lecture? Please subscribe GCS Solutions, like the video if you really like it, share among the friends if you find it useful, and comment for the improvements. We are GCS Solutions, making technology easy to learn. Till next lecture, be intelligent.